Okay, we're already at lecture 7. It's amazing. And this lecture is divided into two. The first part is really short. We're going to finish up the sequential logic design that we started in the last lecture. And then we're going to jump into having fun with hardware description languages, Verilog, which you already started with in your labs, but I'll give you a treatment that will be hopefully useful for the rest of your labs and for, who knows, maybe the rest of your life. Okay, so this is the agenda. I already said this. This is what we're going to do today. And tomorrow, we're going to have a tedious lecture on timing and verification. It's a critically important topic, but maybe very boring for some of you, or very exciting to some of you. We'll see, I guess. But it's a topic that needs to be covered. Okay, and then next week, we're going to start with microarchitecture and architecture levels. We're going to talk about more higher level architecture, one Neumann model, and then instruction set architecture. And then Friday, we're going to look at instruction set architectures even more and do assembly programming. Does that sound like fun? Okay, great. I heard a big yes over there. That's good. Okay, recall that there are extra assignments. I put this because it's going to be due tomorrow. After tomorrow, we won't accept it somewhere over here, deadline. Yeah, there you go. And you know all of this, so I'm going to go through this quickly. And there's another benefit of reading Moore's paper. Everybody talks about Moore's law, but nobody reads the original paper. I think that's a common disease of the days. People talk about stuff. It's easy to talk about stuff on social media, but not many people know the original source of the work. So that's another benefit of reading Moore's paper. It's an optional assignment. You don't have to do it. But if you do it, then you know the original source of what Moore's law is. Okay, and you know what to do. Okay, and these are required readings. I cannot emphasize enough the importance of doing these readings. I mean, I do these readings sometimes myself. I go back to this book, for example, for which we're going to cover chapter 4 today. Not all of it, but I think if you do the readings, you'll understand the lectures even better. And I would suggest doing the readings before the lectures. That's much better for your understanding, because the lectures cover a lot of the material from the readings. That's especially this week and next week's lectures. Later, we'll get into lectures where, unfortunately, there are no textbooks that cover these in good ways. But this is where you can actually do the readings and build the fundamentals. Okay, for tomorrow, hopefully you'll do the timing and verification readings. The lecture will be a lot easier if you actually do these readings tomorrow. And this is only in Harris and Harris, this book. It's decomposed into two chapters. One is in 2.9, and the other is in 3.5. Okay, you don't need to do the chapter 5 yet, but that's going to be useful in the future. Okay, and next week, there are more readings. This is for next week's lectures, and I'll leave these slides. You don't need to do them right now. Just do tomorrow's reading for tomorrow. Okay, this is what we're going to do. We're going to wrap up the sequential logic circuits and design. I'm going to go through a lot of things quickly just to jog your memory, because we've covered everything that I'm going to go through until the point that I'm going to go a little bit more slowly. So basically, sequential logic requires circuits that can store information, and we've seen different kinds of circuits. We start with the cross-coupled inverter, and we talked about it needs control, and then we went into a different kind of latches. We introduced the gated D latch, which is good to control, and then we built sequential logic circuits based on that. And then we said that gated D latch is not enough because gated D latch is level sensitive. Whenever you change the clock to 1, gated D latch actually is transparent. Its output changes while the clock is 1. We don't want that. In a finite state machine, we want the output value to change only at the rising edge of the clock or falling edge of the clock, only when basically the clock changes. And we want the inputs to be stable during the entire clock cycle so that we can operate on them with some delay, which we're going to talk about tomorrow. Delay is very important. But for that, you need a different kind of construct, which is the D flip-flop, right? Flip-flop was the state element we introduced. That's not level sensitive, that's sensitive to the triggering of the edge. Later, we will see the Verilog implementation of the flip-flop in this lecture. And that's how you build finite state machines. And you use flip-flops for the state registers. At the edge of the clock, they capture the next state, and then you can use the value of the state that's coming out of the flip-flop for the entire clock cycle. And this is a finite state machine. This, again, very quickly, because you've seen this multiple times in the last lecture. You need next state logic, flip-flop, that determines what should your next state be, state register to hold the current state, and the output logic to determine what your outputs are. Okay. And we already said what's at the bottom. And then we were doing this example where we were going through the finite state machine of a somewhat smart light controller, but you probably don't want to use that light control in your real lives. Because if it gives access to one lane over here, one avenue over here, and if the traffic keeps happening in that avenue, it'll keep green, right? This is not good. So there's a fairness problem in this controller, but that's okay. We designed it. Somebody designed it. These things exist in real life also. Please don't design things like this in the future, because it's not good for human behavior, I assume, right? If one of them gets unfair access all the time, assuming the traffic keeps flowing. But okay, that's the simple state logic we looked at, and you remember this. What we did was we designed the state machine for this. It was a Moore's finite state machine. Outputs were dependent only on the state and not in the current inputs. And then this is the finite state machine diagram. And then we actually construct the state transition table, which looked like this, if you remember. If you don't remember, go back to the lecture, look at the video. But it's very easy. It's also in your book, actually. This is directly from your book 3.4.1 section. And we constructed the simplified logic for the next state logic. This is actually our next state logic. And then we looked at the output table. We constructed what should the outputs be based on the current state. In this case, it's easy because it's a Moore machine. Current state directly determines the outputs. There's nothing else you need to determine the outputs. And by just looking at this, you can tell this is a Moore machine, because the next state, the outputs are depend only on the current state, as you can see over here. And then we need to encode the outputs. I'm going to talk about that in a little bit. And then this is a logic we designed for the output logic. And then, if you remember, this is a finite state machine. Basically, we designed the output logic and the next state logic. We have a 2-bit state register. And this is our next state logic that we designed. And this is our output logic that we designed. Cool? That's a reminder. Basically, a very quick summary of last lecture. And I said, if you want to go through this, just look at chapter 3.4 from this book so that you remember, you understand the timing. But we'll cover timing a lot more in the next lecture. Okay, so this is where I stop. Basically, let's take a look at what you can do with our finite state machine. Actually, state encoding is one. This is actually important. How do we encode the state bits? That's a key question. Now, in our machine, it's simple, right? We have only 4 states. But you may actually have a real environment where you have millions of states. Encoding may be important in those cases. So there are 3 common state binary encodings with different trade-offs. One is fully encoded, one hot encoded, and output encoded. So if you look at the Swiss traffic light with 4 states, this becomes interesting. If you have 3 states, it's a bit less interesting, but it's still interesting. So let's try to encode the states. So if you see over here, we have 4 states. What is the minimum number of bits you need to encode 4 states? Yes? 2, exactly. It's basically log 2 to the 4. So, and that's our encoding. That's called fully encoded. It's also called binary encoding. I don't like the term binary encoding, but your book used it because everything is really binary encoding in the end, right? You encode things in binary. But this is, I call it full encoding. Basically, you use the minimum number of bits to use to encode all states. Basically, log 2 number of states bits to represent the states. So hopefully this is obvious. Because you have 4 states, you can encode the different states with these. Now, this minimizes the number of flip-flops, right? Because you have only 2 1-bit flip-flops, or a single 2-bit register. But it doesn't necessarily minimize the output or next state logic. There are interesting trade-offs here, which we will not get into. So let's take a look at one-hot encoding. One-hot encoding is interesting. Basically, this says that each bit encodes a different state. So you use number of bits to represent the states. In the previous example, we have 4 states. So we use 4 bits. And exactly 1 bit is hot for a given state. Hot means turned on. High, 1, basically. That's why it's called one hot. So this is example. In this case, the bit 0 is 1, even though we have 4 bits. This is state 1. In state 2, bit 2 is 1. In state 3, bit 3 is 1. In state 4, bit 4 is 1. So there is no, basically these are complete, there's no overlapping ones in any state, which is good because it's simple to design. Basically you have n states, you have n bits, and each state is represented by the turning on of exactly 1 bit. So very automatable. Unfortunately, it maximizes the number of flip-flops. You have lots of flip-flops over here now. But it does minimize the next state logic, which is good. And if you want to convince yourself, you can think about this a little bit. Okay. And then there's the output encoding, which is interesting. This is somewhere in the middle in terms of how many flip-flops you will have. Basically, the idea over here is that outputs must be directly accessible in the state encoding. You have a state encoding, and you can directly access some of the outputs. And this works in this case because we have a Moore machine. Basically, if we have 3 outputs, light color, red, yellow, green, we can encode the states with 3 bits, where each bit represents a color, right? Clearly, we have 4 states, and each state has a 3-bit encoding. And in the red state, you have the bit representing the red turned on, the other ones turned off. In the red and yellow state, you have the bits representing the red and yellow turned on and the other one off. Basically, this is it. I think I've already said what I wanted to say. So this is not minimal, as you can see. It's not 2 bits. It's not maximal. It's not 4 bits. Well, maximal can be infinite, but it's not maximal within reason, 1/2 encoding. As you can see, basically, bit 0 encodes green, bit 1 encodes yellow, and bit 2 encodes red. So this is the case where both bit 2 and bit 3 are turned on. Bit 1 and bit 2 are turned on. As a result, this encodes the yellow and red state. Okay, so hopefully it's obvious. So clear, this is good for minimizing the output logic, because now you're really looking at the outputs and ensuring that outputs are directly accessible in the next state, which means that if you already determined your state, you can basically pull out your outputs from some of those bits. That's why it minimized the output logic. But it only works for Moore machines, because output is a function of the state only. Output is not a function of inputs. Make sense? Okay. Okay, so clearly there are a lot of design choices here, and the designer must choose an encoding scheme that essentially optimizes the design under given constraints. And we're not going to go into this in this course. But the basics you learn could be useful for making trade-offs in the future. Okay, so that was output encoding. You could do something similar in the state encoding, which I'm not going to go into. Basically, if you choose different kind of state encodings, you can actually lead to a different kind of logic in terms of overhead, performance, power, but output encoding is something that you should know. I may ask about it. Actually, there is a question that will come in the future homeworks that may be useful for you to understand the concepts better. Okay, now let me talk a little bit about Moore versus Mealy machines, and then we're going to be done with sequential logic. So recall, this is another slide from last time. We determine the next state by the current state and the inputs. And there are 2 types of finite state machines that differ in the output logic. Moore FSM, outputs depend only on the current state, similar to the output encoding that I showed earlier. That looks like this, basically. If you look at the output, the only inputs are the state, and then you have outputs. And if you're output encoding, this output logic is very, very simple, actually. There's no logic over here. You just pull bits from the state. Mealy FSM, on the other hand, output logic is a little bit more complicated. You get some bits from the current state, and you get some bits from the inputs, and then you determine the outputs. Clearly, any machine can be Moore or Mealy, actually, and there are transformations that you can do. Let me actually give you an example of this. It's best understood with an example. Does anybody know a person named Alyssa Hacker? Yes? Who knows Alyssa Hacker? Nobody's doing the readings? Okay, people who are doing the readings should know Alyssa Hacker, because I don't know a real Alyssa Hacker. But it's a fictional character in your book. In this book, at least, yeah, not in the other book. I'm sure there are great hackers for Alyssas, but not with this name. Okay, so assume that this hacker has a snail that crawls down a paper tape with 1s and 0s on it, and the snail smiles whenever the last 4 digits it has crawled over is 1101. Basically, we're going to design a machine that does exactly this. Whenever you see a sequence that looks like this, 1101, you basically smile. So smile is an output. It's a 1 or 0. And the input is every bit that you see. In every state, you get 1 bit input. So basically, Moore FSM will look like this. States will determine the outputs, and Mealy FSM states will not directly correspond to the outputs. And this is the Moore FSM in this case. Basically, you have 5 states. So this is the reset state. You start with this one. And then if you've seen a 1, you transition to the state where you've seen only 1. If you see another 1, you transition to the state where you've seen 1, 1. If you see a 0, you transition to the state where you've seen 1, 1, 0. If you see another 1, you transition into the state where you see 1, 1, 0, 1, and at that point the output is 1. So this is the output. In all these states, the output is 0 because you have not seen a sequence of 1, 1, 0, 1s. In this state, you've seen a sequence of 1, 1, 0, 1, so your output is 1. So clearly the output is a function of only the state over here, right? And if, of course, you can, if you've seen a 0 in this state where you've seen only a 1, you go back to the state where you haven't seen anything because you're looking for a pattern 1, 1, 0, 1, right? So it's beautiful, nice. Mealy FSM is a little bit more complicated looking. Basically, you encode the input that you get and also the output you should have. So if you're in the reset state, if you've seen a 1, you transition to state 1 over here, which means something, but your output is 0 because you haven't seen 1, 1, 0, 1 yet. And then if you see another 1 over here, you transition to this state, but your output is still 0. If you see a 0, you go into this state, and your output is still 0 because you haven't seen 1, 1, 0, 1. And then if you see 1 over here, it turns out you go to this state again. The state encodes you've seen 1, which is what you've done actually, because the last thing you've seen is really 1 over here. And then you output a 1. You smile because you've already seen 1, 1, 0, 1. And then you also record that you've seen a 1. And then if you see another 1 again, you go to this state because you've seen 1, 1 now. And then your output is 0. So this is more compact, as you can see. You have only 4 states. In this case, you have 5 states. So if you encode your outputs directly inside your states, there's a correspondence between your outputs and the states, then you will usually have more states. And that's a trade-off. You have more states here. You have fewer states here, so you have fewer bits in your state register. But this looks a bit more complicated. Now your output logic is not as easy. Output logic is a little bit more complicated over here. You cannot take stuff directly out of your state bits or have little output logic. So that's the trade-off really here. So hopefully this gives you an idea of how to design finite state machines actually. Actually, this is an interesting example because a lot of the Turing machines initially were designed based on this sort of finite state machine logic, and as a result, people developed a lot of complexity theory based on things being read from a tape. But if you take a computational complexity course, you will understand that much better. I assume you haven't taken a computational complexity course yet, right? Yes, you will in the future. Okay, so let me finish with the finite state machine design procedure very quickly. Basically, if you want to design a finite state machine, you first determine all possible states of your machine, and start with a state transition diagram. Generally, you start with a textual description and then put that onto a state transition diagram. Of course, you need to determine your inputs and outputs for each state and figure out how to get from one state to another. And then the approach is you should start with the initial state. What is the initial state of the machine, or a finite state machine, and what happens from it? Okay, I said that. And then continue to add transitions and states. Picking good state names is very important, especially if you build complicated state machines. Actually, this is much like programming. It's not programming exactly clearly, because we're not programming, but it's somewhat like programming. You have a sequential control flow, like a program with conditionals and gotos, and every state has some meaning. Hopefully it should have some meaning based on the logic of the machine, of the program that you're trying to write. So there are if then else constructs, for example, based on the input, you go to this state or this state. That's an if then else construct, right? Or you can have a simple if construct, else may be remaining in this state, right? And the outputs are controlled by the state or the inputs, and we know that already. So in hardware, typically we have many, many concurrent FSMs. So there are many finite state machines. There is a finite state machine for memory. There's a finite state machine for different parts of the processor, like control of the cache or control of the processor itself. And these sometimes interact with each other. So there are actually points where they interact. So it may become a bigger finite state machine also, but some of them may be completely independent of each other also. Okay, so what is to come? This is just to foreshadow what's coming next week. So next week we're going to see a data path of a very simple processor. It's called the Little Computer 3. It's basically a processor developed for instructional purposes. Nobody builds these processors. But it's very good for instruction and understanding. And you've already seen many components of it. So finite state machine over here controls basically what is the next state of the machine. What should the machine be doing in this particular cycle? So it gives you a lot of control signals over here. And these control signals go and determine the inputs to different data path components like muxes, registers, multiple registers, that register files, incrementers over here, which inputs you should use, what should you do in your arithmetic logic unit, which you will see also next week. If you're doing the readings, you may have already seen it actually. And this is a simple bus over here. You've seen the tri-state buffers over here. For example, different components can actually put values on this bus, and then they can communicate with each other. So there's also memory over here. And we're not going to cover input and output, but it uses the same principles of the combinational and sequential logic. So basically, with the building blocks that you've seen so far, combinational and sequential, you can build this. The key will be designing the finite state machine, of course. That's one of the keys. So this will come, and then, actually this is in the next 2 weeks. Next week we will start with this, and then we're going to go over the data path of this and understand how this operates, how you can execute an instruction by sequencing through different states in the different state machines, in the state machine. Okay. Any questions? Otherwise, I'm going to transition into the next lecture.